Is this all for chapter 18?
11.8.
Yes.
Yeah.
11.8. Wow.
13 clubs, 13 hearts, 39 52 mark total, 4 face cards, king, queen, jack. Queen, king, and jack.
Yes.
Okay, I need a review on this.
Yeah.
It's bad. All this dices and cards everywhere. Dices. Do you like that?
Dicey.
Oh.
Okay, so today we're going to finish chapter 11 by doing the last section that we're going to cover, 11.8. Most of this, the math gets a little mathy. You like that? Mathy and wordy. But once we actually do an example, yeah, don't get intimidated by the definitions of conditional probability. Once you do an example, I think it's going to make sense. So we're going to talk about finding probability of 2 or more independent events all occurring. So we're looking at independent events occurring at almost simultaneously or one after another. They're independent of each other.
So like dice and cards.
Yes. Then we're going to look at the probability of 2 or more dependent events all occurring. So if the first event changes the probability of the second event, it's a dependent event. If the first event doesn't change the probability of the second, they're independent. And we'll do good examples. A lot of times we'll do probability with replacement or probability without replacement. If I'm drawing 2 people at random, if I do one with replacement or one without replacement, that's going to change depending on the first draw if I don't replace it, right? If I think of playing a deck of playing cards, if I'm going to draw 2 cards and I draw the first card, if I don't replace that card, it changes the deck, right? So that's what we're going to look at. If I replace that first card, then the probability doesn't change from one event to another event. And then the last thing we're going to look at is conditional probabilities. So the definition of independent events, the probability of consecutive events depends on whether the first event affects the second. Right? This is an independent event. The definition of independent is event A has no effect on event B. Okay? We're looking at independent versus dependent. An independent event means event A does not affect event B. I talk about flipping coins. If I flip a coin and land on heads and I pick it up again, does it matter what I landed on the first time? No. It's not going to change the probability of getting heads any given time. So those 2 events are independent. If I flip a coin and roll a dice, independent events. It doesn't matter. Event A's outcome does not change the probability of event B occurring. Rolling a dice and getting a 6 and rolling a second die and getting a 3, those are independent events. Rolling a dice and getting an even number, those are dependent events. If I know I got an even number, that changes the probability of getting any number on the dice, right? And that's what eventually we're going to kind of lead to. If I roll a dice and tell you it's even, I say, what's the probability that's a 3? If I roll a dice, it's 1/3, right? But if I tell you it's even, that changes the probability that it's a 3, or the probability it's a 2, or the probability it's a 6. So that's along the lines of some things we're going to do. Dependent events means knowing the outcome of event A changes the probability of event B happening. An example, drawing from a deck of cards by not replacing it, then drawing a second card. Parking in a no parking zone and getting a parking ticket. If you park in a no parking zone, the probability you're going to get a ticket is higher than if you just park somewhere. If you know you parked in no parking zone, the probability you're going to get a ticket is greater, right? So that's kind of what they're saying there. Knowing information about event A can change the probability of it happening if the events are dependent on each other. Like if I tell you I rolled the dice and got an even number, that changes the probability of it being 1, 2, 3, 4, 5, or 6, right? So the multiplication rule here, when we're looking at independent event, we're looking at the probability they both occur. What's the probability of A and B occurring? So a lot of times event A and event B, they're two separate events. What's the probability of getting an ace and drawing a 6 of hearts? So you do the probability of A times the probability of B. This is kind of where the tree diagram comes in, right? If I said, I want my first card, here there's 52 branches, but all I care about the first branch and then the second branch. And we're going to multiply that and we want the probability of A and B. So we have to be a little careful on this chapter 11 test because the probability of A or B is different than the probability of A and B. Because or we're going to add them, right, and subtract any overlapping. But and we're going to multiply them. So let's look at this example. A coin is flipped and a dice is rolled. Find the probability of getting heads on the coin and a 4 on the die. So we're looking for the probability of getting heads and a 4. So that's the probability of getting heads times the probability of getting a 4. So 1/2 times 1/6, which is 1/12. Which makes sense because there's 2 outcomes for heads or tails. There's 6 outcomes for the dice. So there's 12 total outcomes. If you were to look at the tree diagram, they're all evenly weighted, evenly distributed, and each one has a probability of 1/12. Does that make sense kind of from when we talked about the tree diagram? Here, the tree diagram, we only care about the branch heads, then a 4. So if we draw it this way, we're looking at that. Any questions on that? Well, let's look at this experiment here. We have a psychology experiment in perception and memory. Colored balls are picked from an urn. The urn contains 3 red balls, 2 green balls, and 5 white balls. The ball is selected and its color is noted. Then it's replaced, and the second ball is selected and its color is noted. Find the probability of selecting 2 green balls. So the tree diagram we care about is getting a green ball and then getting a green ball. The key here is every time I pull out a ball, I replace it, right? So what's the probability of getting the first one being green?
1/5.
So there's 2 green out of 10. So I could put 2 out of 10, or I could simplify that to 1/5. What's the probability of getting the second one green? 1/5. 1/5, right? Because I replaced that green one. So that would be 1/25.
I don't understand where the 25th comes from.
Because I multiplied a 5th times a 5th. So I multiplied the numerator 1 times 1 and the denominator 5 times 5. So these are just a 5th times a 5th.
Okay.
Which is 1/25. If you do 2 out of 10, you can do 2 out of 10 times 2 out of 10. 2 out of 10 times 2 out of 10 would be 4 out of 100, which is 1 out of 25.
I guess in the wording, I didn't realize we needed to do it twice. I didn't think A was asking for it twice.
A is saying you're selecting 2 green balls.
Right.
So the first branch would be your first green ball, and your second branch would be your second green ball.
Okay.
B is saying selecting a green ball and then a white ball.
All right.
So this one is going to look like, I'm running out of room here. a green ball, and then a white ball. So what's the probability of getting a green ball?
1/5.
What's the probability of getting a white ball? 1/2. So this would be 1/10. And if you put 2/10 times 1/2, it's going to simplify to 1/10. So you want to reduce these. So the probability that I reach in there and get the first one being green, put it back, mix it up, and pull out a second one and it being white is going to be a 10th. Selecting a red ball, then a green ball. So I look at the tree diagram of getting a red one and then getting a green one. So what's the probability I get a red one?
3/10.
3/10. And what's the probability I get a green one? 1/5. So that's going to be 3/50. Kind of see the process there. The tree diagram is a lot bigger than this, but we only care about the branch of getting a red one and then getting a green one. So we do the probability of red times the probability of green, and we get the probability of this branch.
So we're just focusing on one single branch of the tree.
Exactly. You're focusing on one single branch of the tree diagram. We only care about the branch of green, green, or red, green. The thing in this section is you have to be very careful if it's being replaced or not. Because if it's being replaced, the probability is going to be the same every time. But if it's not, the probability of getting the second one being green, you have to reduce how many green ones are if you got the first one being green. And we'll do some examples of that. And a lot of times it will tell you, note, and it's replaced. So what's the probability of getting 3 kings?
3 over.
So king, king, king. What's the probability of the first king? 1/13 if I want to reduce it. What's the probability of the second one being a king? 1/13 or 4 out of 52. And the third one being a king? 1/13. So 1/13 times 1/13 times 1/13 is 1 over
2,196.
I wouldn't bet money.
So that's saying if I have 52 cards and I pick one at random, write it down, put it back in the deck, shuffle it, pick another one at random, write it down, put it back in the deck, shuffle it, and pick another one. The probability that all 3 of those were kings is going to be 1 over 2,197. What about 3 clubs? What's the probability that I get a club?
1/4.
Clubs. So the first probability is a 4th. The second one's going to be a 4th, and the third one's going to be a 4th, right? So I get 1 out of
64.
64. You guys see that?
So I assume
Generally, mathematically, it's going to be easier when you reduce them first versus having a really large number at the end to reduce. However, if your calculator reduces fractions, it doesn't matter. You can put in 4 out of 52 times 4 out of 52 times 4 out of 52, enter, and then reduce your fraction. If you have a decimal or fraction button, it'll give you that answer. So there's more than one way to write it.
so if you were to draw a card and keep
Mhm.
it,
Yes,
those consecutive
are going to
fractions
change.
would be different.
Yes, and we're going to look at examples of that. Those are dependent events because the probability of the next card depends on what that first card was. So we have this poll. 47% of all parents in America with children under 18 feel frequent stress. If 3 parents are chosen at random, find the probability that all 3 will say they feel frequent stress. Right? 47% of them, so the probability that you pick someone at random and they feel stress is 47%. So what's the probability if you pick 3 people at random? What's the probability they feel stressed? It's the same approach, right? Stress, stress, stress. So this is 0.47, 0.47, 0.47. You never deal with you don't want to deal with percents because a probability is always between 0 and 1. So if it gives it to you in a percent, you have to convert it to a decimal. So we get 0.104. So this is saying 10%, if I pick a group of 3 people, or if I just pick 3 people at random, 10% of the time, all 3 of them are going to feel stress. Again, this looks really scary, but it's not. So like we said, in events that A and B are dependent, if we would know the probability of A and B, we take the probability of A times the probability of B given that A has already occurred. So we talk about the green example of pulling out the green ball in the urn, the probability that both of them are green, I take the first one, maybe there's 5 green ones out of 10. Then the next time I reach in, the probability is going to be 4 out of 9, right? Because you have to decrease the number of green ones and the number of total because you hold on to that one. So this would look like the probability of B given that A has already occurred. In an independent event, this would be the same as the probability of B because it doesn't matter if A occurs or not. But in a dependent, probability of B changes depending on what A is. So this would be an example of not replacement. Okay. So we still use the multiplication rule, but there's a little minor modification. And honestly, when you're doing these problems, you don't even think about the modification. You just think, okay, what's the probability of A? Now, what's the probability of B given A's happen? In independent events, it's going to be the same as the probability of B. In dependent events, it's going to be different. So let's look at this example. Appliance store gets shipment of 25 plasma TVs. 3 of them are defective. If 2 of the TVs are chosen at random, find the probability that both are defective. The first TV is not replaced. So I want a defective TV and a defective TV. So what's the probability my first TV is defective? What is it? 3 and 25, right? Because there's 3 defective out of the 25 total. Now I've picked a TV and I've taken it off the shelf and I put it in my cart. I'm going to pick another TV. What's the probability that another one I picked is defective? I know the one I picked is defective. 2 24ths, right? And I can write that as 1/12 to make my algebra a little easier. Right. Key here. Decrease the numerator and you also decrease the denominator because there's not 25 TVs up there anymore. There's only 24. And only 2 of them are defective because I have the defective one in my cart. For that branch, that's what I'm thinking. I'm thinking I got the defective one and that probability was 3 out of 25. Now I'm going to pick another one. What's the probability that one's defective? Well, there's 2 defective left out of 25 total, and that's going to simplify to 3 over 25 times 12. So here, 3 and 12, 1. This would be 4, so it would be 1 over 100. But you don't have to do it that way. You can use your calculator. So what would 25 times 12 be? 300? Mm-hmm. So simplifying that, I get 1 over 100. It doesn't, you could have taken 3 times 2 and got 6, and 25 times 24 and got 600, and it would be 6 over 600, which simplifies to 1 over 100 again. that make sense there? You can see, I mean, a lot of times the keywords will be with replacement or without replacement. Let's look at this next example. Again, you might even want to like kind of box or underline if it says not replacement or with replacement. So in this case, what's the probability of getting 3 jacks?
3 out of 52.
So the first, what's the probability of getting the first card being a jack?
1 over 13.
1 out of 13 or 4 out of 52. Oops. 1 out of 13 or 4 out of 52. I'll write 4 out of 52 on the bottom. What's the probability that the next one's a jack, given the first one was a jack?
1 over 17.
3 out of 51. I don't know if that simplifies.
To 1 over 17.
Is it 1 out of 17?
Yeah.
1 out of 17.
Subtract the 1.
Yeah, so there's 4 jacks, right? So if I got the first one a jack, I only have 3 left. Originally I have 52 cards, but I drew that first card, so now I only have 51 cards. A lot of times when you leave it like this, it's a little easier to see what's going on. What's the probability the next one's a jack? 2 out of 50 or 1 out of 25?
Yep.
So this approach here might make it a little easier to see what's going on, but the approach on top is going to make your algebra a little easier. Because 1 times 1 times 1 is going to be 1. 13 times 17 times 25 will be your denominator. However, if you plug in 4 divided by 52 times 3 divided by 52 times 2 divided by 50 and hit enter, and then you change your decimal to a fraction, it should give you the same as taking 13 times 17 times 25, and then 1 over that. So you can play around with your calculators, see whatever you're comfortable with. What do we get? 1 over 13 times 17 times 25?
1 over 5,525.
5,000, what is it?
525.
525. All right, 5,280. How many feet are in a mile? Any questions on that? B, getting an ace, a king, and a queen in that order. So what's the probability I get an ace?
113.
1/13. We're 4 out of 52. What's the probability I get a king? Given the first card's an ace. 4 out of 51. It's not the same, right? Because from the first card, I went from 52 to 51. Now I have 50 cards. What's the probability it's that card's a queen, given the first one was an ace and the second one was a king? 4 out of 50.
Can you still write
The reduced one? Okay, so let's, yeah. Let's do that on the bottom. So this would be 4 out of 52. This would be 4 out of 51, and this would be 4 out of 50. So this would be 1 out of 13. 4 out of 51 reduce? I don't think it does. 4 out of 50 is 2 out of 25. I don't think that reduces anymore. So like I said before, it should be a little easier to see what's going on when I don't reduce them, because there's 4 aces out of 52 cards. But then I draw that ace, and I have that in my hand. Now I have 51 cards in the deck, and 4 of them are kings. Because the first one was an ace, so I still have 4 kings. Does that make sense? So then the next one, I only have 50 cards in the deck, and I want to know what's the probability of being a queen. And there's still 4 queens left, because I have an ace and a king in my hand. Make sense? So the 3 jacks we did, the ace, the queen,
What if it said
and the
getting
king.
an ace, a king, and a queen without saying an order?
Then you would have to do the different permutations of ace, king, and queen.
Gross.
You'd have to add them up. So you would, the first one, ace, king, queen, and then you could do ace, queen, king, and there are 6 different permutations. So you'd add up those probabilities. So here we get 8 over 16,575. However, if you did those 6 permutations, all of them are going to be the same, right? What about getting a club, a spade, and then a heart? Probability I get a club,
1/4.
1 out of 4, or 13 out of 52, and they're gonna keep it not reduced, and then they're gonna reduce it and do the multiplication. What's the probability of it being a spade? 13 out of 51, and the probability of it being a heart, 13 out of 50. You guys see that? If they reduce the first one to 1/4, the other 2 don't reduce. Multiply that, and they get 169 divided by 10,200. Really, the key here is the setup. And then can you push the right buttons in your calculator? Can you set up 13 over 52 times 13 over 51 times 13 over 50, and then multiply that in your calculator and reduce it and get 169 divided by 10,200. So if you're having problems with your calculator reducing, let me know and I can show you how to go about that. And then D, all 3 clubs. So what's the probability of the first one being club times the second one being club times the third one being a club? It should make sense that the numerator decreases each time because I'm getting a club. So there's only 12 left, then there's only 11 left. I start with 52 cards, there's only 51, then 50 left. So these are what are known as dependent events. The probability is going to change based on what the first card was. I still kind of like to draw it out so I know, oh, the first card was a club, the second card was a club, and the third card was a club. So I'm going to decrease my numerator and my denominator by 1 each time. Sometimes you're just reducing your denominator by 1 in the event that clubs, spades, and hearts, those are all different categories. And they get 11 divided by 850. You don't have to do any of the neat tricks, reducing, simplifying. If you do, that's fine. Your calculator should be able to handle it by plugging in 3 numbers on top and the 3 numbers on bottom, taking the top number divided by the bottom number, and then reducing it. It should give you 11 out of 850. Any questions on that? The last thing we're going to look at is a conditional probability, and a lot of times these are given in charts. They give you a chart, and then they say, given the person picked at random was a female, what's the probability that they said the TV on or the television was too violent? What's the probability that someone picked at random said the television was too violent? A lot of times you see these in published papers all the time, and it depends on how many people were surveyed. And they say, you know, they'll break them up by age group from 18 to 25, 25 to 30, all these different age groups. And they say this specific age group, the probability was a lot higher than this age group or whatnot. That's known as a conditional probability. A lot of times it's denoted as the probability of B happening given A is happening. So what's the probability that they said the television was too violent given they were a female? Okay. Or what's the probability the television was too violent given they were a male? This is what's known as conditional probability.
We don't have that in our notes.
It should be on the back. Is it multiplication? Did I not get the conditional probability one? All right, so you might I can, yeah, right. You don't have to write down. Basically, you get this and write down. We call, this doesn't really come up much because you're looking from a chart. But it could come up where I say the probability of A and B happening is this, and the probability of A happening is this. And we'll see examples. Sorry about that, guys. I don't know how this one got left off.
What's the line? Outline?
It's saying, you can always say given that A has happened. So what's the probability of B given A? So you assume A has happened. That's like what I was saying with rolling the dice. If I roll dice, I say, what's the probability of it being a 6? You say 1/6, right? Well, if I roll that dice and say, what's the probability of being a 6 if it's even? I tell you it's an even roll. It changes to 1/3. That's what's known as a conditional probability. What is the probability of B happening given A has happened? So A is the event you know has happened. The roll was even. So what's the probability of being a 6? A lot of times you see like games and they give you 3 doors and they say, pick a door at random. So the probability you get the biggest prize is a 1/3. And then they show you a door and they say, do you want to change? Because your probability has changed now from a 1/3 to a 1/2. So it's the conditional probability here. The probability of B given A has happened.
Wait, you switch doors.
I don't. They say that you have better odds if you don't switch doors.
Really?
The Monty Hall problem. Yeah, there's a lot of problems like the games and
The TV show.
brain teasers with that is, do you switch doors? And then they look at the probability. At first it's a 1/3, but now one door is shown. Does the probability change that it's going to be the winning door? Because now it's a 1/2 instead of a 1/3. So let's look at an example. Suppose your professor goes stark raving mad and chooses your final grade from A, B, C, or D, F, or incomplete, totally at random. Find the probability of getting an A given that you get a letter grade higher than a D. So you know you're going to get something higher than a D. What's the probability of it being an A?
Would be 1/3.
It would be what?
1/4.
Would be one. It's higher than a D.
Oh, so it is incomplete is not higher than
Incomplete is not higher than a D.
So it'd be 1/3.
It'd be 1/3, right? Does that kind of make sense where it's saying, if basically it's changing your sample space. Originally, your sample space was A, B, C, D, F, or incomplete. There's 6 choices. But if somehow you figured out it's higher than a D, your sample space then changes from 6 choices to 3 choices. Either A, B, or C. Make sense here? You're changing your sample space. You're changing the total number of possibilities. The same thing with rolling the even dice.
So you just dropped it from 6 to 3.
Well, the probability of getting an A, granted it's higher than a D, your book uses a little bit different notation. I'm going to go ahead and show you what your book uses. It should make sense that it's 1/3 that they go through. Yeah, so they kind of go through, you can set it up this way. The probability of getting an A is a 6, divided by the probability of getting something greater than a D is 3/6. So simplifying this, you get 1/3. I don't really prefer this way because it's a little messy. So this is what it's saying. What's the probability of A and B divided by the probability of D? Getting an A and being higher than a D, there's only one thing that's an A higher than a D. So there's 1/6 there. Divided by the probability of getting a letter grade higher than a D, which is 3/6. Flip and multiply, and you get 1/3. 6 cancel, and you get 1/3. I don't necessarily, a lot of students get confused on this. The only time it comes in handy is if I give you the probability of A and B, and the probability of D and not give you a word problem. Then you just take the probability of A and D, or in this case, we didn't really name it, but getting an A and getting a letter grade higher than a D divided by getting a letter grade higher than D. And we'll do an example of that, I think, where I only give you those two pieces of information and you have to divide them to come up with the probability. But most of them are going to be in this form. Hate crimes are defined to be crimes in which victims are targeted because of one or more personal characteristics, such as race, religion, sexual orientation. So here's a table from 2007 at the FBI motivation for certain crimes reported. So we have this motivation, crimes against the person, crimes against property, and crimes against society. So they said there's 3,031 crimes against people that were motivated by rape, 421 that was motivated by religion, and so forth. Right?
Ours looks different.
We have numbers on ours, just, I don't think we need those.
14.
You have extra numbers. Yeah, when Word formatted it, it decided to make this number 9, 13. Yeah, you know when you have the number, sorry about that, guys. Just erase the question numbers. You see it now? Those don't mean anything. It's just saying, for some reason, it put the table as a question number and every input as a question number. So here it's reading the graph. Find the probability that a hate crime was racially motivated given that it was a crime against a person. Good, right? So I only care about that it's a crime against a person, that it was racially motivated out of the total crimes against people, right? So this is going to be 3,031 divided by 4,491. That may or may not simplify. But do you see how that information is gathered from the graph? You're not looking at the total crimes, which would be this number plus this number plus this number. Right? The probability that it was a hate crime against a person would be this number divided by the sum of the totals. If it says given that, a lot of times given that is a key that it is a conditional. That there's some condition that you know about. Right? Given that, it's in this category. So how many is in that category divided by the total in that category? So B, find the probability that a hate crime was against property given that it was motivated by the victim's sexual orientation. Against the property, so we know the overlap of sexual orientation and properties, right? That it was motivated by sexual orientation. So where's my total? This doesn't have a total for sexual orientation, does it? Does yours have a total column?
No.
No. That would be kind of helpful. Given that it was motivated by the victim's sexual orientation, how many crimes were motivated by the victim's sexual orientation? All these were motivated by victim's sexual orientation. So ideally, we'd have total over here. I think maybe it gets there. 14. Okay, so the top number is the hate crime is against property, and that is motivated by sexual orientation. So the top number is 418. The bottom number would be this number plus this number plus this number.
Those against property.
Find the probability a hate crime was against property, given that it was motivated by the victim's sexual orientation.
So would it only be the middle one?
This 418?
Yeah, over the 3,158.
3,158 was meaning it was a crime against property.
That's what, so it's against property, against all sort of
Okay,
sexual
yeah, sorry.
orientation
Eventually, yeah,
crimes?
yeah. That's what we're. The hate crime was against property, given that it was motivated by the victim's sexual orientation. Let's go to, no. Here, it's gonna be, what do you know? What's given? Go back to B here. The given part was that it's motivated by the victim's sexual orientation. So we're looking at this category, sexual orientation. Given that, that's what comes after the given that, that's the kind of your category you're in. Part A was saying, given that it was a crimes against a person. So we're looking at the crimes against the people there. Do you see that? The given that is kind of your key. What comes after the given that tells you what category you're in. Given that it was a crimes against a person means it was motivated by race. So you have crimes against person and race, where they overlap, divided by the crimes against the total crimes against people. B is worded just a little differently, but very similar. Go back to the B wording. Given that it was motivated by the victim's sexual orientation. So our category is the sexual orientation. We want to know how many of the people that commit that crime was motivated by sexual orientation, how many of those were crimes against property? So it's actually really easy to find the numerator and a little bit more difficult to find the denominator. The denominator is the total of the category after the given that part. Make sense? A little bit different there. So here they don't tell us. A lot of times they'll have a total column over here. But if you add up 1,039 plus 418 plus 3, you get 1,460, which gives you a percentage here.
So would we take that 29%?
So it would be about 29% or 28.6%. It's approximately, so. Which makes a little more sense. So you have to be careful a lot of times when you read things, how it actually works out. You know, crimes against society, you know, if I were to look, 7 out of 12% of crimes against society are racially motivated. Versus if I say crimes, what percentage of crimes are racially motivated? Or if I say, given that it was against society, what percentage of that was racially motivated, religiously, or sexual orientation motivated? So if we look at the homework from this section, a lot of them will have tables. A lot of times it's men or women. I think you do this example. This has to do with minutes on a cell phone usage. So out of the category here, less than 600 minutes, 600 to 800, 800 to 1,000, or more than 1,000 minutes. So the student talked less than 600 minutes given that it was a woman. What's the probability that they talk less than 600 minutes given that it's a woman? Given that it's a woman tells you you're in this category. So 61 divided by this number plus this number plus this number plus this number. Because you know it's a woman. What's the probability they talk less than 600 minutes? That's a conditional probability there.
So the given that's just gonna be our denominator, basically.
Yeah, the given that is your denominator, and it's the total of whatever category it is. So it could say, given that they used between 600 and 799 minutes, what's the probability it was a woman? So how many women use between, so that would actually end up being a half, which would be 18 divided by 18 plus 18. So the given that is a key that it's a conditional. If I said, what was the probability someone was picked at random was a female, you'd add up all the females divided by the total number of people surveyed, which in this case is 200. There's no conditional. Sometimes there's no conditional. So I'm going to pass out your pre-test 2, which will be similar to your test 2 that I will give you on Friday. On Wednesday, your homework is due for chapter 11.
That was your Friday.
I will collect them
No,
after
she does it
class,
the
so if
day
you want
before.
to ask any
Bullshit.
questions, you can. I will also post the answer keys to the pre-test on Wednesday and go over any questions anyone has on the pre-test.
If we don't have school on Wednesday, will we still have to test Friday?
Good question.
What, it's supposed to snow Wednesday? Oh, yeah. it's just like-
Probably so, because I don't want to wait until after spring break to give you the test.
That would be bad.
If we don't have school on Wednesday, I will record a lecture going over these and answer email questions. If anyone has questions on that. I don't foresee it being a problem, because I don't foresee us not having school on Wednesday, because I don't think it's supposed to rain a lot.
I don't
Is
know.
it all- yeah.
Still in the
Okay.
So we will probably.
I don't know,
It's
like,
supposed to rain and then freeze and then snow and then
Yeah.
freeze again.
I've always just wanted to enter.
Okay, what's the probability we're gonna have school?
the probability, no, maybe I'll give you,
Extra credit.